Hi, we're going to talk about the road not taken in etheric electromagnetism. So this is combining the ether notion, a fluid of some sort, the ether, that would support propagation of electromagnetic energy. This came about in the following way. I'm going to present my idiosyncratic view, and you can take it with a grain of salt, but you'll see where I'm going as we get into this. In the 1820s, 1830s, people like Ampere, Volta, Faraday carried out a series of experiments that showed there was basically a lot of underlying order to electricity and to magnetism, and they were in some sense related, different sides of the same coin. So what happened was a German, Grossman, looked at all this stuff and he was trying to make sense out of it. And he came up with the notion of what is today called exterior calculus. And he started off by saying, well, let's take a function, say, of 3 space dimensions and 1 time dimension. So we have this function. And what we're going to do is compute the gradient of the function. So that means we're going to compute the partial derivative of that function with respect to each of the 4 dimensions, 3 for space and 1 for time. So let's just stop and look at this. The 3 spatial dimensions will denote by X, Y, and Z, and the time dimension doesn't have the units of measurement of length of meters. So we have to multiply it by something that converts it that way. We're going to multiply time by the speed of light. So this will take the speed of light multiplied by time to give us the 4th dimension, except that we're going to do a little zinger here. We're going to multiply this by the square root of -1. So our 4 variables are going to be X, Y, Z, and I, the square root of -1 CT. So we're going to compute now the gradient with respect to X, Y, Z, and ICT in each of 4 directions. When we take this scalar function, which we're going to call the gauge function, and compute that gradient in each of the 4 directions, we come up with a 4-dimensional potential. The first 3 spatial components have to do with an electric or a magnetic potential, and the 4th one, is a little different. We'll just leave it that way. So that's where Grossman started. Then he said, well, now that we've taken the gradient, we've looked at the rate of change of this function in each of these 4 directions. Let's look at the rate of change of the rate of change. So let's look at the gradient of the gradient. And in doing this, that led to taking this potential function that he just computed, and he came up with a series of fields now that were in these new directions. Then he said, okay, now let's do the gradient of the gradient of the gradient. And that took us to currents and current densities, and also charge densities, magnetic and electrical. And finally, he said, okay, let's compute the gradient of the gradient of the gradient of the gradient. And that took us from these current densities down to what I'll call sources that would be driving everything. So he did all this in 1847, published it all. It was totally incomprehensible to anybody. We fast forward to 1860s, early 1860s, and Maxwell's looking at all of these different experimental observations and so forth. And he basically comes up with what Grossman came up with, a set of equations, which are now called Maxwell's equations. And he realized that what came out of this set of equations was there was a possibility for transverse propagation of electromagnetic energy, a transverse wave. So the wave would go this way, and perpendicular to it would be a magnetic field and an electric field. Typically, they'd be rotating around it as the energy propagated in this direction. And this was done theoretically, which immediately suggested to all kinds of people that they should be looking at something to support this wave propagation. We have water and we have waves in water. So if you have waves going through space, then there must be some ether that makes up space that allows these things to propagate. And here's where the zinger happened. Two people, Michelson and Morley, carried out some experiments in the middle 1880s at Case Western Reserve. The nature of the experiments was it showed that if we looked at the propagation of light, which is what was felt to be coming out of Maxwell's equations, that the propagation of light had no preferred direction. That is, they looked at light going up, down, right, left, you name it, and there was no wind blowing that pushed it in any way, which is what they expected to see. So they then jumped to the conclusion, this is the interpretation of the data, is where the error occurs, that there was no ether. Now, there actually is an ether. If you talk to any physicist today who is involved in quantum mechanics, quantum deals with discrete activities, discrete particles of all sorts, and in particular, the discreteness of space. So space itself is viewed as a foam, a discrete series of compartments. They rub against each other. They hold particles. Particles move by hopping from compartment to compartment in space. And so there really is an ether, but this was thrown out with the Michelson-Morley experiment. So if we stopped and looked at what's going on here with what Grossman did, with what Maxwell did, we'd realize that we probably need to augment the equations with something that does reflect ether, and those sorts of augmentations come out of fluid mechanics. So it was known in the 1900s. You can look in Sommerfeld's books on mathematical physics. There's a whole series of books there, and he makes it very clear that you have the equations for electromagnetism and the equations for fluid mechanics. And the only difference in these, when the tire hits the road, is there's an extra set of terms in fluid mechanics that reflects the nature of the fluid, the density of the fluid. And so if this were in fact included in Maxwell's equations, which was done by Nikola Tesla, undoubtedly, then what you would find is a unified set of equations, and the density of the ether, the density of space, would change from place to place. The density of space inside the sun is probably different than the density of space outside our solar system, for example. So the nature of the density is going to be a tip-off as to something related to gravity is where we're heading. So what was missed here was taking the original Maxwell's equations or Grossman equations and combining those with the equations of fluid mechanics, and then doing what's called a perturbation expansion. If you take the density of space, the density of the ether, and you do an expansion here of these merged entities, the two electromagnetism plus the etheric, the fluid side of things that goes with it, you can expand it with the 0th order term, a first order term, a second order term, and the density being so small that as we go to high, we can ignore everything beyond second order. The 0th order term is simply going to give us Maxwell's equations. But the first and the second order terms, when you carry this out, give us the strong force, which is the force that binds like to like. Protons, for example, are positively charged. Normally, they would repulse one another, but close enough to one another, they attract in the nucleus of atoms. And the weak force, which is also found in the nucleus, a neutron will decompose into an electron and a proton and a neutrino. And the weak force, therefore, allows us to get isotopes of different sorts. So we end up with this perturbation that leads to Maxwell's equations. We get the strong force, we get the weak force, and we also get, by looking at the changing densities, gravity. And what happens to gravity is the density changes. And this is what someone like Tesla ran with and did some amazing things. This is the road not taken, and long story short, this probably was discovered by all kinds of people and has been suppressed. With that, we will call it a day.